Hey students, welcome. This is a video on infinite sequences. Now, infinite sequences are basically a list of numbers. It's an ordered list of numbers separated by commas that goes on forever. Okay? And each number is called a term of the sequence. Okay? So, infinite sequence is an ordered list of numbers. Well, actually, that's the definition of sequence. Okay? So a sequence is an ordered list of numbers, and a sequence can either be finite, which means it has a countable number of terms, or it can be infinite, and we're focusing on the infinite ones here. Okay, so an ordered list of numbers, each number is called a term of the sequence. Okay, so each number is called a term of the sequence. And remember, infinite sequence means it goes on forever. Okay? And if it were a finite sequence, which we're not really going to be doing much of, but if it's a finite sequence, then that would mean it would only go so far, and then the list of numbers would eventually stop. Okay? So examples are the best way to learn for most people. So let's see an example of an infinite sequence. And these are very useful. They show up all the time in different applications, such as physics, biology. They even show up in video game design and programming, because many times you'll have things that are appearing, such as certain patterns that appear in the game, and those patterns can be written as sequences. So they're very useful in programming, actually. Okay, so example, we're going to have a bunch of different types of examples in this section. And in our first example, they say a formula for the nth term, okay, a formula for the nth term of an infinite sequence curly brace a sub n curly brace. Okay, so this right here is the sequence notation. It's got a curly brace, and then it says a sub n, a with a subscript of n, and then it ends the curly brace. This right here is a sequence notation. Okay, so they're saying a formula for the nth term of an infinite sequence a sub n is given. Okay? All right, and they want us to find the values of the first four terms of the sequence. Okay? So find the values of the first four terms of our sequence. And again, the way we're writing our sequence is a curly brace, and then a sub n, and then we put another curly brace on the other side. Okay, so that's a lot of instructions, but basically they're going to be giving us a formula for the sequence, and we need to find the values of the first four terms. I misspelled 4. I mean the number 4, not F-O-R. Okay, so find the values of the first four terms of a sub n. Okay, and what they give us is they tell us that a sub n equals -1 parentheses to the n plus 1 divided by 10n minus 5. Okay, so this right here is the formula. This is called the formula for the sequence. Formula. And what it represents is you can plug in different values for n, and it will tell you what that term is. And since we want to find the first 4 terms, that means we need to find a1, a2, a3, and a4. Those are the first 4 terms. So sequences generally start at 1. So n equals 1, n equals 2, n equals 3, and n equals 4. Okay, so what's that going to look like? Well, our first term is going to be a sub 1. It's going to be a sub 1. Okay, and basically all you do here is you need to recognize that a sub n equals -1 to the n plus 1 over 10n minus 5. And so basically a sub 1 is the same formula, it's just everywhere you see an n, you plug in 1 instead. Okay, that's going to give us the first term. So we get a sub 1, or a1, is -1 to the 1 plus 1 all over 10 times 1 minus 5. Okay, so literally all we're doing there is we're plugging in 1 for n into the formula. And then of course you want to simplify this. Okay, so if we simplify this, 1 plus 1 is 2. Okay, and then -1 squared is -1 times -1, so the minuses cancel. So that minus goes away and we get +1 in the numerator. And then in the denominator, 10 times 1 is 10, minus 5 is 5. So our first term is 1/5. Okay, that's our a1, or a sub 1. When I say sub 1, I mean subscript of 1. So it's a with a subscript. That little number on the bottom right corner is called a subscript. So a1 is 1/5. And then we wanted to find the first 4 terms. That was the first term. So if the first term is a1, the second term is a2, and so forth. Okay, so here our second term is a2. Actually, let me give myself a little more room there. So second term is a2. Okay, and a2 is going to be -1 to the 2 plus 1 all over 10 times 2 minus 5. Okay, so it's the same exact formula as we did for a1. It's just here we're plugging in n as 2 right there and right there. Okay, and that's going to give us our second term. Okay, so for our second term, we have -1 to the 3. And remember, if you raise a negative to an odd power, it's always going to be a negative. Whereas if you raise it to an even power, it's always going to be a positive. So like here, -1 cubed is the same as -1 times -1 times -1. So 2 of the minuses cancel, but one of them's left over. So -1 cubed is actually -1. Okay, so here in the numerator we have -1. And then in the denominator, 10 times 2 is 20, minus 5 is 15. So we get -1 over 15. And if we bring the minus out front, that's the same as -1/15. Okay, and that's actually our second term. Okay, that's a2, which is our second term. And then of course we keep going because they asked for the first 4 terms. So we still need to do a3, and A4. Okay, so A3, using the same formula, is going to be -1 to the 3 plus 1 all over 10 times 3 minus 5. Okay, so -1 to the 3 plus 1 is going to be -1 to the 4. And because 4 is actually an even power, that minus is going to go away. So remember, if you're raising -1 to an odd power, the minus stays. And if you're raising -1 to an even power, the minus goes away. Okay, so that's going to be +1 on the top. And then on the bottom, 10 times 3 is 30, minus 5 is 25. So we get 1 over 25. And that's our third term. Okay, that was our third term. And then we just have to do one more for this problem. We need to do our fourth term. Okay, so our fourth term is A4. So plugging in 4 for n, we're going to have -1 to the 4 plus 1 all over 10 times 4 minus 5. Okay, so 4 plus 1 is 5, and 5 is actually an odd power. So remember, a negative raised to an odd power is always negative. And if you don't believe me, you can just write it out. -1 to the 5th power is -1 times -1 times -1 times -1 times -1. 4 of the minuses are going to cancel, but there's going to be one minus left over, so that's going to be negative. Okay, so we're going to have -1 on the top, and then on the bottom, 10 times 4 is 40, and then 40 minus 5 is 35. So our denominator is going to be 35, and then if we bring the minus out front, we actually get -1 over 35. Okay? And you might have noticed something about this problem. So looking at this sequence, notice that the first term was positive, the second term was negative, the third term was positive, and the fourth term is negative. So it's alternating in signs. We call that alternating signs because it goes from plus to minus in each term. And the reason that happened was because of the -1 to the n plus 1. So whenever you have something like -1 raised to a power, this alternates the signs. So we call this alternating signs because each term changes sign from positive to negative or negative to positive. Okay, so that's that should be pretty helpful, I hope. And most people don't find these that difficult. Once they understand them, they're usually pretty straightforward. So you have a couple of those on your homework. And most of them are pretty self-explanatory, so I'll go ahead to the next type of problem. Okay? So, we found the first 4 terms, we're done. Let's take a look at a new example. So this example is going to have different instructions. So for our next example, we're still going to be working with infinite sequences. But for this one, instead of giving us a formula and asking us to write the first few terms, in this one, they're giving us the first few terms, and we have to come up with a formula. And most people find these more challenging. Okay, so example, find a formula. Find a formula for the nth term of the sequence below. Find a formula for the nth term of the sequence below. Okay, so when you're doing your homework, make sure you read the instructions. On the last problem, they gave us a formula, right? They said, a formula for the nth term of an infinite sequence, a sub n, is given. So given means they gave you the formula, and they wanted us to find the values of the first few terms. Well, this next problem, this next example, we need to find a formula for the nth term, and they give us the sequence. Okay, and because this is trickier, I wanted to do at least a couple examples of this one. So for our first example, example number 1, we're going to have a formula of, well, I'm sorry, not a formula. We need to find a formula. The first few terms of the sequence are going to be 10, negative 10, positive 10, negative 10, positive 10, and then they write dot, dot, dot. So the 3 dots at the end means that it's an infinite sequence, so it goes on forever. Okay, so this is actually how you can write a sequence if you don't have the formula for it. Okay, on the last one they gave us a formula. With this one, we don't have a formula and they're asking us to come up with one. So like I said, these can be trickier, but the basic idea is you want to write, in order to come up with a formula, you have to be a little bit creative and you have to figure out a pattern. So what I usually do is underneath each term, I write what the term is. So for the first term, that's A1. The next term is A2. Third term is A3. Fourth term is A4. Fifth term is A5. Okay, so that's actually using the same notation we did on the last problem. Now, so realize that those are the terms of A sub n, okay, or an. And so here, n actually equals 1 for the first term, n equals 2 for the second term, n equals 3 for the third term, n equals 4 for the fourth term, n equals 5 for the fifth term, and so on. Okay, so what your goal is, our goal is find a general formula that represents this sequence. Okay, so we need to find a general formula A sub n. So we know A1 equals 10, A2 equals negative 10, A3 equals positive 10, A4 equals negative 10, and so forth. And for each of those terms, we know that n equals 1, n equals 2, n equals 3, n equals 4, and n equals 5. So the way I usually do this is I try to come up with a pattern. So how do I get from 1 to 10? How do I get from n equals 1 to 10? Well, let me erase these a sub 1, a sub 2, and all that. So my question is, how do I get from 1 to 10? Well, to get from 1 to 10, I need to multiply by 10. I think we can all see that. Okay, so here I need to have something times 10. So here for the first term, I actually have 1 times 10. And this is just me trying to find a pattern. Now for the second term, how do I get from 2 to 10? Well, 2 to negative 10. Well, I could do 2 times negative 5. Right, I could do that. But I'm probably going down the wrong track here. Because once I get to 3, what am I going to have there? Then I'm going to have 3 times what gives me 10? Well, I'd have to write it as a fraction. So we're not on the right track here. So instead of multiplying, we're going to have to try a different approach. Okay, so multiplying by these numbers was not working. So now we try something new. And these are a lot about experimentation. When you've done a few of them, you might be able to think of the formula right off the bat. Well, one thing that you might want to notice is that each term here is alternating in signs. So like I said up above, to alternate in signs, that means you're going to end up having negative 1 raised to a power. So maybe we should have that as part of our formula. Okay, so let's see what we can do there. So to get from 1 to 10, we could have negative 1 to the 1 plus 1. Right? So where did I come up with the 1 plus 1? Well, somehow I need to have the 1 there. So I'm saying negative 1 to the 2, or negative 1 to the 1 plus 1 is going to be positive 1. And then what else do we need there? We also need a 10. Okay, so instead of having it as things multiplied together, I'm having a power of negative 1 times 10. And then how do we get the second term? Well, here, to get from 2 to negative 10, we're going to follow this same approach. So we're going to have negative 1 to the 2 plus 1. Okay, so negative 1 to the 2 plus 1 times 10. So I'm noticing a pattern here. I actually have a good pattern here. So if I plug in 2 there, I get negative 1 to the 3, which is actually going to be negative because it's an odd power. And then negative 10 actually gives me that. Okay, and then for 3, I get, if I give myself a little bit more room, for 3, I can see the pattern is continuing. So it's negative 1 to the 3 plus 1 times 10. So there I'm plugging in 3 in the formula. Okay, so we noticed that there was alternating signs, so we went ahead and we wrote it as negative 1 to a power times 10. And the reason we keep multiplying by 10 is notice that 10 is actually the number for all of these. All that's really changing from each term is we go from plus to minus to plus to minus. And that's how we got that power of negative 1. Okay, so I think we can see a pattern here. So this number that I'm circling here, that's the same as n, and that's what we're ending up plugging in there. So here our general formula is going to be a sub n equals negative 1 to the n plus 1 times 10. Okay, negative 1 to the n plus 1 times 10. Or people usually write the negative 1 to the n plus 1 at the end. So you could also write it. Remember, the order doesn't matter when you're multiplying. So you could also write it as a sub n equals 10 times negative 1 to the n plus 1. And that's actually how they write their answer on my math lab. They write it that way. So now, as you can see, these are a lot trickier, because you have to look for a pattern, and not only that, then you have to come up with your own formula to describe the pattern. But remember, when you have alternating signs like this, when it goes from minus to plus, or vice versa, that's always going to be negative 1 raised to a power of n. So it's either going to be negative 1 to the n plus 1, or it's just going to be negative 1 to the n. So either way, that's always going to give you the alternating signs. And then you can focus on the numbers for the rest of your formula. Here the number was the same for each term, so that's why I just kept writing 10. Okay, pretty cool, huh? I actually really enjoy these because they're a bit of a puzzle. So if you like puzzles, they can be nice. Okay, so let's take a look at another problem. So that was our formula that we got there. Now that one was pretty easy. I'm not going to lie, these can get harder. So for problem number 2, our sequence is negative 1, comma, 16, comma, negative 81, comma, 256, comma, negative 625, comma, dot, dot, dot. So once again, what I recommend you do is you first write down what n is for each term, and then you try to get from n into this sequence here. All right, so writing that down, I think we used blue last time, right? Oh, we use red for n, and then we use blue for the arrows. Okay, so for n, we've got n equals 1, comma 2, comma 3, comma 4, comma 5, comma dot dot dot. Okay. And so we're looking for a pattern here. And I'm going to try doing this one in a little bit different way because this one's harder. So what I'm actually going to do is, instead of trying to write the pattern directly, I'm going to work through step by step and try to figure out things individually. So I'm going to try to get closer and closer to those numbers. So first of all, we're looking for a formula a sub n. And for the first term we have a negative, for the second term we have a positive, then a negative, then a positive, then a negative. So we do see alternating signs here. But if n equals 1, it has to be negative, which means we're actually going to have a negative 1 raised to the first power for our first term. Okay, let me write that a little bit smaller. So for our first term, we have negative 1 raised to the 1. For the second term, we have negative 1 raised to the 2. For our third term, we have negative 1 raised to the 3. For our fourth term, we have negative 1 raised to the 4. For our fifth term, we have negative 1 raised to the 5. And you can check to make sure that's correct, because negative 1 to the first power is negative 1, so we're good there. For the second term, negative 1 squared gives us positive. Negative 1 cubed gives us negative, and so forth. So these are correct. Okay, so we're good for the negatives and the positives. Now the tricky part with this problem is how do we get, from 1 to 1? Well, we're going to have 1 right here. For the second term, we have 16. For the third term, we have 81. For the fourth term, we have 256. And for the fifth term, we have 625. So now we're looking for a pattern with these other numbers. So 1, 16, 81, 256, and 625. So what is the pattern there? Well, the pattern I see there is we have powers of some number. And the powers are going to be, well, any number to the 0 is 1. And so what's the number that we're doing powers of here? Well, it could be tricky, but I think it's going to be n raised to a power. Because if you think about it, n to the 1, n raised to the 4th power might work. So n raised to the 4th power might be our ticket here. So let's try, if we write it as 1 to the 4th power, and then the next one is going to be 2 to the 4th power, and then the third one is going to be 3 to the 4th power, and then 4 to the 4th power, and then 5 to the 4th power. Let's see if that works. And if you can't think of it in your head, you can experiment with different ways of writing the numbers, but we're looking for a pattern here, and I think this is the pattern. So because 1 to the 4th is 1, 2 to the 4th is 16, 3 to the 4th is 81, right? Because 3 times 3 is 9, times 3 is 27, times 3 is 81. And then 4 to the 4th, if you aren't sure about it, you can check it on a calculator. So clear 4 to the 4th is 256, so we're good there. And then 5 to the 4th is 625. So that's good. We have figured out the pattern. Now you could try other things. If you can't think of them right off the bat, you could just try different ways of writing the numbers. So, there's got to be a pattern there somewhere, and I was able to pick it out right away. But if you can't do it right away, don't stress. You just try different things until you find a pattern that actually works. Okay? So what we got here is we actually have negative 1 to the 1 times 1 to the 4th negative 1 to the 2 times 2 to the fourth, and so forth. Now, negative 1 to the 2 is the same as negative 1. We don't need to write plus or plus anything, so we're just going to leave it as negative 1 to the 2. Sorry, I was thinking it was like the last problem, but it's not. Okay? So as we can see here, we have a nice pattern. So let's circle the places where we're plugging in n. So it looks like we're plugging in n equals 1 right here for that exponent, and then right here for the base. Same thing for 2. If we're plugging in 2, we have 2 for this exponent right here, and then we have 2 for this base right there. Okay, so I think we're seeing a pattern. Well, we already have the pattern, so how do we write it as a formula? It's going to be a sub n equals negative 1 to the n times n to the fourth. Okay, negative 1 to the n times n to the fourth. And I know this way that I wrote this time took longer than the last one, but most people find this way easier because even though you have to write more, it's less confusing. So on the last one, we could have done it the same way, but the last one was easy enough that most of us should probably already be able to see every term is 10, so all that's really changing is the exponent of the negative 1. So that last one was easier anyway. But with a harder one like this, I recommend my method, my approach here. Okay, so that's our answer. A sub n equals negative 1 to the n times n to the fourth. And notice the difference between these two formulas on problem number 1 and problem number 2 is for problem number 2 we had negative 1 to the n because the first term was negative, whereas on problem number 1 we actually had negative 1 to the n plus 1 because the first term was positive. Okay, so get used to the idea of n plus 1 for your negative 1 if your first term is positive and it's alternating, whereas if your first term is negative and it's alternating, then that's usually going to be negative 1 to the n. Okay, and this is how they write their formula on my math lab. So that's pretty cool. And then there's one more thing I wanted to talk about before we go on to the next problem, is these sequences don't always have to start at 1. They could start at 0, they could start at 2. I guess they might even be able to start at negative 1, although that's very rare if that ever happens. But because they can start at different numbers besides 1, when you're actually writing the formula like this, I almost forgot, we actually need to write n is greater than or equal to 1. So when it's a sequence, it's assumed that n is going to be an integer, which means a counting number. But you do need to write n is greater than or equal to 1 so that they know that n starts at 1, so it doesn't start at 0 or 2 or negative 1, whatever the case may be. And I should have done that for the first problem as well. Okay, so I should have written n is greater than or equal to 1, and that's because the first term was a1, so n started at 1. Okay, so let's do another example. Let's do another example. So this is example number 3, and for this one, we've got 1 over 10, comma, 3 over 15, comma, 3 squared over 20, comma, 3 cubed over 25, comma, dot, dot, dot. Okay, so this one is interesting. It doesn't have any pluses or minuses, so this one is not going to be alternating signs. It's not actually that hard of a problem, but setting it up can be a little bit a little bit tricky. So remember, we're going to be starting at n equals 1. So we start at n equals 1 unless they tell us otherwise. So here's n equals 1, n equals 2, n equals 3, n equals 4, dot, dot, dot. Okay, so just like I did on the last problem, I'm going to be looking for a pattern. Now this actually is a fraction, and we can see it looks like there's a pattern on the top, and then there's a different pattern on the bottom. So let's focus on the numerator first. So for the numerator here, it looks like we have 1, 3, 3 squared, and 3 cubed. Well, this is actually kind of nice because they already kind of gave us the formula. So here we can see 1 is the same as 3 to the 0. And then, so 1 is 3 to the 0. And then 3 to the 1 is 3. And then we have 3 squared and 3 cubed. Okay, so that's a good place to start. And that's our numerators. So we can see a pattern there. And then for our denominators, it's a different pattern. So for the denominator, when n is 1, we get 10. When n is 2, we get 15. When n is 3, we get 20. When n is 4, we get 25. Now that's a little bit trickier. For that one, it's looking like we don't have powers. It's looking like we're adding 5 each time. So if we're adding 5 each time and we start at 10, then we could be saying something like we could have something like maybe 5 plus 5 times n. Now the reason instead of writing n, I should be writing 1 here. So we got 5 plus 5 times 1 is 10. 5 plus 5 times 2 is 15. And 5 plus 5 times 3 is 20. And then 5 plus 5 times 4 is 25. So that looks like our pattern there. And you might be wondering, well, how did I know to write it as 5 plus 5 times n? Well, I noticed that it started at 10, but it's increasing by 5 each time. So I thought of, well, if the first term is going to have n equals 1, then it makes sense that we would have to do 5 plus 5 times 1, because 5 plus 5 is 10. Okay, and then for the second term, 5 plus 5 times 2 is 5 plus 10, which is 15. And then 5 plus 15 is 20, 5 plus 20 is 25, and then we got a pattern. However, we don't have a perfect formula yet. So as we can see, there's some interesting stuff going on here. So first of all, notice that our powers here don't actually match up with n. So how do we get from 1 to 0, 2 to 1, 3 to 2, 4 to 3? How do we get to those? Well, how do you get from 1 to 0? You subtract 1. How do you get from 2 to 1? You subtract 1. So what the formula is we're actually going to have 3 to the 1 minus 1 for the first term. And then for the second term, we're going to have 3 to the 2 minus 1. And then 3 to the 3 minus 1. And then 3 to the 4 minus 1. Okay, and then we can see that we're actually plugging in the correct thing. Because we're actually plugging in n there. So now we're good. So here we're plugging in 1 there. We're plugging in 2. Here we're plugging in 3, and so forth. And then also our denominator, we don't have to worry about it too much because it's already written in a form that we need. So in the denominator we have 5 plus 5 times 1. Well, there we can see we're plugging in 1 right there. And then we have, for the second term, in our denominator we have 5 plus 5 times 2. So there we're plugging in n is 2. Okay, so I think we get the pattern. Okay, we definitely should be getting the pattern here. And we have it written in a way so that we can write it as n. We can write it in terms of n. So those places where I've circled in red, those are the places where we're going to be writing n. Okay, so what we got here is our formula is going to actually be a sub n equals 3 to the n minus 1 over 5 plus 5n. All right, so that one was more complicated than the others. So I'm glad I did an example of it. It is quite similar to the one in your homework though, so hopefully you'll be good with that. The one in your homework just basically the same setup with different numbers. Okay, cool. So I wanted to continue. It's a long section that we're working on here. The next thing I wanted to talk about is sequences and whether they converge or diverge. Okay. So a sequence converges if its limit exists. So if the limit as n goes to infinity of a sub n exists and is finite. Okay? So a sequence converges if its limit, the limit as n goes to infinity of a sub n exists and is finite. So remember, finite means it actually has to be a number. So it has to be something like 3 or 0.7 or negative 12. It can't be infinity or negative infinity. And it has to exist, which means you have to be able to find the limit. Okay, but actually these are really easy because basically what you end up doing is you just find the limit of the sequence, and then if that limit exists and is finite, then you're done. And if it doesn't exist, or if the limit is plus or minus infinity, we say that the sequence diverges. Okay, so otherwise, so if the sequence does not converge, otherwise the sequence diverges. So diverges just means it does not converge. And this is important because when you're studying sequences, you need to know what's happening as you go to infinity. Because they're infinite sequences, it's important to know what the overall pattern is. And if you take the limit as n goes to infinity of that, that's going to give you that pattern. Okay. So let's see some examples of finding whether a sequence converges or diverges. So example, new example. Determine whether the sequence a sub n converges or diverges. Okay. Find the limit. Find the limit if it converges. Okay. These are actually a lot of fun. I always thought these were very straightforward. So, problem number 1, example number 1, they tell us that a sub n equals 5 plus 0.5 raised to the n power. Now, literally, all you have to do here is find the limit as n goes to infinity of a sub n. And even though a sub n has counting numbers, you know, it's 1, 2, 3, 4, it's not continuous. Even though that's the case, it turns out that you can still just take a limit just as if it were the limit as x goes to infinity of an expression involving x. Okay, it works the same way when you're calculating the limit. So because that all works out, we can literally just do limit as n goes to infinity of 5 plus 0.5 to the n. Okay? And you can just distribute that limit to each of those terms. Okay, you can distribute it. Okay, so we get the limit, and remember, when you're distributing a limit, you basically just plug in and then figure out what happens. So what we've really got here is 5 plus the limit as n goes to infinity of 0.5 to the n. Now with 0.5 to the n, remember that 0.5 is actually the same as 1/2. So instead of writing 0.5 to the n, I'm going to write it as 1/2 to the n. And then we can actually distribute the n, excuse me, we can distribute the n to the numerator and the denominator. Okay, so we have 5 plus the limit as n goes to infinity of 1 to the n over 2 to the n. But 1 to the n is just 1. Okay, so we don't need that. So we really just have the limit as n goes to infinity of 1 over 2 to the n. And so as n goes to infinity, 2 to the n goes to infinity. But 1 over infinity, if you will, is 0. So if you have a finite number over an infinity, that's going to go to 0. So this whole thing, this whole limit is going to go to 0. This whole limit is going to go to 0. Because you got that finite number on the top, and then on the bottom you're going to infinity. So because the denominator becomes infinite, the numerator becomes infinitely small, and it goes to 0. But you've seen that many times before. Okay, so here we just have 5 plus 0, which is 5. Now because we got a finite number as our answer here, we say that the sequence converges, and it converges to 5. Okay, so the sequence converges. The sequence converges to 5. Because it converges to whatever the value of that limit is. Sorry, I forgot to brush my hair today. It's getting pretty messy. I just noticed that looking on the camera. Okay, so the sequence converges because it actually has a finite limit. And the limit also exists. Okay, and in general with these, realize that if you have a decimal between 0 and 1 and you raise it to a power, that's always going to go to 0. So let me add that as a little note over here. Note the limit as x goes to infinity of a to the x equals 0 if a is between 0 and 1. Okay, because if you have a power of any decimal between 0 and 1, you can always write it as a fraction like we did here. And then the denominator is going to grow faster than the numerator, so that's always going to go to 0. Okay, just like we saw here. Okay, cool. So that's our first new example. So let's take a look at another one. Example number 2. So for this one, our a sub n equals, this time they're using curly braces, which doesn't really change anything. A sub n equals curly brace 8n plus negative 1 to the n all over 8n. Okay, so 8n plus negative 1 to the n all over 8n. And what we have to do here is, once again, just take the limit as n goes to infinity. Okay, so the limit as n goes to infinity of 8n plus negative 1 to the n over 8n. There's a couple ways you could do this problem. One way is you could divide the top and the bottom by 8n, and then the other way would be to split it up into two fractions. Either way is fine. I'm just going to go ahead and divide the top and the bottom by 8n because that's a pretty standard way to do these. So in other words, I'm going to multiply the top and the bottom by 1 over 8n. Okay, so I'm going to multiply the numerator and the denominator by 1 over 8n. And remember, if you have an infinite limit like that and you're trying to calculate it, you can basically just divide the top and the bottom by the highest power. So here the highest power is 8n. Okay, so if I distribute the 1 over 8n on the top, I end up with 1 plus negative 1 to the n over 8n. And then on the bottom, I also have 1. Okay, and this is still the limit as n goes to infinity. So as you can see, if you divide the top and the bottom by the highest power, it just makes the limit a lot easier to find. So we divided everything by 8n, and now we just have 1s there. And then this one, the question is, what happens here? Well, as n goes to infinity, 8n also goes to infinity. So this goes to infinity. But then the thing is, negative 1 to the n just goes negative 1, 1, negative 1, 1, negative 1, 1. Well, even though it's bouncing back and forth, it's still a finite number. So it's still negative 1, positive 1, negative 1, positive 1. It's not growing to infinity. So that means you once again have a finite number over infinity, and that's always going to go to 0. So this whole thing here is going to go to 0. So really, we just have 1 plus 0 all over 1, which is 1 over 1, which is 1. Okay, so the value of our limit is 1, and it converges because that limit is a finite number. Pretty cool, huh? So that's good to know how to do. And then you have another problem similar to that in your homework. I'm going to skip that one. Okay. So let's see another example of one of these. Okay, so I guess that was example number 2. So this next one's going to be example number 3. So for example number 3, our a sub n equals n squared plus, sorry, let me pull it up on my notes. Sorry, it's n squared minus, my bad, n squared minus 14n plus 49 all over n minus 7. Okay? And if you read what they say on My Math Lab, it's kind of strange the way they do it. So I'm going to show you my way, which is just way easier. Okay, so what we got to do here is we need to find the limit as n goes to infinity. Limit as n goes to infinity of n squared minus 14n plus 49 all over n minus 7. Okay, and again, the way My Math Lab does it is very strange. They use epsilon and delta, which we're not going to do. That's just too complicated and unnecessary for just calculating a limit. Okay, so what we're going to do is we're going to divide the top and the bottom by the highest power in the denominator. Okay, so the highest power in the denominator here is n. Okay, so divide numerator and denominator by highest power by the highest power in the denominator. In the denominator. Okay, and that's just the same trick we did on the last problem. So what's the highest power in the denominator? Well, we can see that that's n. Okay, so we're going to be dividing the top and the bottom by n, which is the same as multiplying the top and the bottom by 1 over n. Okay, so we multiply the top and the bottom by 1 over n, which is the same as dividing by n on the top and the bottom. And then we distribute the 1 over n on both the top and the bottom. So on the top we get n squared over n. If you subtract the exponents, that's just going to give you n. So we have n minus 14 plus 49 over n. That's in the numerator. And then in the denominator, we have 1 over n times n is 1, minus 7 over n. So the limit as n goes to infinity here, well, the 49 over n is going to go to 0 because the denominator is going to become infinitely large, so it's going to go to 0. And then the same thing in the denominator down here, this negative 7 over n is also going to go to 0. But then this problem is a little bit different than the other ones because we still have this n left over in the numerator. Okay, so we really have the limit as n goes to infinity of n minus 14 over 1. And any number divided by 1 is just the number. Okay, so this is actually just going to be n minus 14. So what's the limit as n goes to infinity of n minus 14? Well, that's, in quotes, that's infinity minus 14. Well, infinity plus or minus any number is still infinity. I put it in quotes because it's not really, you can't really subtract or add a number to infinity. But that's still going to be infinity. That's what's important. Okay, and because infinity is not a finite number, we say that the sequence diverges. Okay, so because infinity is the value of the limit, that's not finite. Well, that means the sequence diverges. Remember, in order to converge, the limit has to exist, and the limit also has to be finite. It can't be infinity or negative infinity. So the sequence diverges. Pretty cool, huh? So that's the good stuff right there. And believe it or not, there's still some more tricks on these, so I need to do at least a couple more examples. So that one we just did was number 3, right? Okay, so that was number 3. So the next one is number 4. So for number 4, we have a sub n equals -1 plus -1 to the n. Now this one is tricky. This one is very tricky. It's actually easy if you know what you're doing, but it's very tricky unless you know the trick. So what we're doing here is the limit as n goes to infinity of -1 plus -1 to the n. Okay, -1 plus -1 to the n. So now, how on earth do you do this? Well, the thing is, as n goes to infinity here, what's really happening is this sequence is just going to keep repeating the same pattern. This is not going to go to 0. It's not going to go to any number. So one way we can do this is, because it's a tricky problem, we can just write out the terms and figure out a pattern. So this doesn't approach anything. And when I say it doesn't approach anything, normally when you're finding a limit, if it's going to converge, it has to be getting closer and closer to a number, or it has to be going to infinity or negative infinity. But let's just write out the terms. So write out the terms. So what are the terms of this sequence going to be? Well, the first term is going to be -1 plus -1 to the 1. So that's -1 minus 1 is -2. The second term is going to be -1 plus -1 to the 2. So that's -1 plus +1, which is 0. And then the third term is going to be -1 plus -1 to the 3. So that's going to be -1 minus 1, which is -2. So I think we're starting to see the pattern already. The fourth term is going to be -1 plus -1 to the 4, which is going to be -1 plus 1, which is 0. And so we got a pattern. So the pattern is -2, 0, -2, 0, -2, 0. Okay? So we got -2, comma 0, comma -2, comma 0, comma -2, comma 0, comma -2, etc., etc., etc. So this is an interesting problem, and I wrote out the terms because we couldn't really just plug in infinity here, because -1 to the infinity doesn't actually have a value. But what we did is we figured out the pattern. And the real question here is this pattern approaching any number? Well, it's not. It just bounces back and forth between -2 and 0, but it's not getting closer and closer to a number. Now remember, to converge, a limit has to actually be approaching a single number, or it has to be approaching infinity or negative infinity. Well, to converge, it has to be an actual number. It can't be infinity or negative infinity. So the thing is, this isn't approaching anything, so the limit does not exist. Limit doesn't exist. So the limit does not exist. And some people like to write DNE. That just stands for does not exist. Okay, so if the limit does not exist, that means we can't calculate it because it doesn't exist, which means that the sequence diverges. Because remember, to converge, it either has to approach a finite number. So the limit has to exist, and it has to be a finite number. And here it does not exist. So the sequence diverges. Okay, sequence diverges. Ooh, so that's an interesting one. I'm glad I did that because that probably would throw people off on their homework if I didn't do that one. Okay, and then there's another problem it's a little bit tricky, but it's pretty similar to the ones we've done. Just remember, if you have a fraction, divide the top and the bottom by the highest power in the denominator. Okay, so you should be good for that one. Now, I did want to do another problem that has the same business going on here. So for problem number 5, example number 5, we have a sub n equals negative 1 to the n plus 1 divided by 4n minus 7. So now this one is interesting. It's a lot like the last problem in that it has that negative 1 raised to a power of n. So you would think that this one would diverge too. You would think that, but that's not actually correct. So if we take the limit as an goes to infinity, sorry, the limit as n goes to infinity, I'm getting tired, this video is pretty long. Okay, so the limit as n goes to infinity of negative 1 to the n plus 1 divided by 4n minus 7. Well, the thing here is that we do have this fraction, and we need to divide both the top and the bottom by the highest power in the denominator. So here the highest power in the denominator is n, so we're going to multiply the top and the bottom by 1 over n. Okay, and then on the top we're going to have negative 1 to the n plus 1 over n, and on the bottom we have 4 minus 7 over n. Okay, so now here's the interesting part. In the numerator, you would think that this would diverge, right? You would think that this would, because it goes between negative 1 and positive 1 and negative 1 and positive 1, you would think that would diverge. However, because it's divided by n here, that n is actually going to infinity. So this is going to infinity. The numerator is just oscillating. So this one is going to be negative 1, positive 1, negative 1, positive 1. Well, actually, I think it starts by positive 1, negative 1, positive 1, negative 1. So that's not actually going to anything. It's oscillating, but the denominator is becoming infinitely large. So that whole thing is actually still going to 0. I know it's weird, but because we're going from 1 to negative 1, it doesn't matter because our denominator is going to infinity, so the whole thing is going to 0. That's tricky, right? And then in our denominator, we should all know by now that negative 7 over n, because the denominator is going to infinity, that one's going to go to 0 as well. Okay, so what we have here is in the numerator we have 0, and in the denominator we have 4 minus 0, which is 4. Okay, so we really just have 0 over 4, which is 0, because 0 divided by any non-zero number is 0. Pretty cool, huh? Okay, so this video is getting quite long, and I am tired, but I gotta keep going. Just as if I were teaching face-to-face. So, that was number 5, and because that answer was 0, 0 is a finite number, so this sequence actually converges. Okay, so the sequence converges. And what does it converge to? Well, it converges to 0. Because 0 is a finite number, and the limit exists, So the sequence converges to 0. So I just wanted to do 2 or 3 more examples, just to make sure you're good for your homework. So for number 6, example number 6, we're going to take a look at a sub n equals the square root of 4n over n plus 9. And again, the reason I'm doing so many examples here is I really don't like the way my math lab does these problems. It makes them seem way too difficult. Okay, they're really quite simple problems. So what we want to do here is we want to find the limit as n goes to infinity of the square root of 4n over n plus 9. Okay? And actually what you can do here is you can once again, just even though it's inside of a square root, you can once again divide the top and the bottom by the highest power in the denominator. Okay, so here inside of the square root, we can see that the highest power in the denominator is n. So we're going to multiply the top and the bottom by 1 over n. And we're actually allowed to do that inside of the square root. So that's what I'm going to do there. And the reason I'm allowed to do it inside of the square root is 1 over n divided by 1 over n is just 1. So we're multiplying the inside of the square root by 1, but that doesn't change anything. It's just rewriting it in a different way. So in the numerator, the n's cancel out. In the denominator, when we distribute, we're going to wind up with, for the first term, we're going to have 1. And then for the second term, we're going to have 9 over n. Okay, so we have 1 plus 9 over n on the bottom. And then on the top, we have 4. Okay, so we have the limit as n approaches infinity of the square root of 4 over 1 plus 9 over n. Okay, and then 4 and 1 are just constants, so the limit of those is the numbers. And then on the bottom, even though it's inside of the square root, the 9 over n is going to go to 0 because the denominator goes to infinity. Okay, so this right here is going to go to 0. And then we've taken our limit because there's no more n's left over. So we're just left with the square root of 4 over 1, which is root 4, which is 2. Okay, so our answer is 2, and because 2 is a finite number, we say the sequence converges to 2. The sequence converges to 2. All right? So if you know the trick, that one's pretty easy. Okay? And I'm just going to do a couple more. So number 7. Okay, number 7 is a sub n equals sine of parentheses 3 pi over 2 minus 6 over n. 3 pi over 2 minus 6 over n. Okay, and once again we're going to find the limit as n goes to infinity of this. So limit as n goes to infinity of sine of 3 pi over 2 minus 6 over n. Well, if you go ahead and look at the negative 6 over n, that denominator is going to go to infinity, which means negative 6 over n is going to go to 0 because the numerator is finite. Okay, so the negative 6 over n goes to 0. So that for that limit, this is actually really easy. We just end up with sine of 3 pi over 2. Okay, so I'm not going to pull up the unit circle, but 3 pi over 2 is actually the negative y-axis. So that's actually going to give us -1, because sine is the y-coordinate, and we're at 270 degrees, which is the negative y-axis on the unit circle. So this is going to give us -1. And once again, because that is a finite number, this sequence also converges. Okay, so it converges to -1. Pretty cool, huh? Okay, so just one more. Uno más. Okay, so that was number 7. Number 8 is actually a sub n equals n divided by 2 to the n. Okay, and we want to find the limit as n approaches infinity of n divided by 2 to the n. Now, this one can be confusing to people, and actually the way they do it on my math lab is actually really good here to make it less confusing. So the problem is, if we do it the way it's written, we're going to get indeterminate. So this is going to give us infinity over infinity, which is indeterminate. Remember, if you either get 0 over 0, or if you get infinity over infinity, that's indeterminate. I did not write that very well. It's because I'm tired. Okay, indeterminate. So indeterminate just means you haven't determined the answer. The answer is undetermined, which means you're not done. It just means you have to keep going. So what we're going to use here is we're actually going to use L'Hopital's rule. Whenever you get an indeterminate, you go ahead and use L'Hopital's rule. Okay, and L'Hopital's rule, remember, all you do is you take the derivative of both the numerator and the denominator. Okay, so taking the derivative, we get the limit as n goes to infinity of, in the numerator, the derivative of n is 1. And then in the denominator, I don't know if you remember this, but the derivative of 2 to the n is actually going to be ln of 2 times 2 to the n. So it's just like the derivative of e to the x is e to the x, but the derivative of 2 to the x is actually ln of 2 times 2 to the x. So you end up with an ln of 2 there. Okay? And then from that, all we have to do is find this new limit. So the ln of 2 is actually a constant, so we can factor it out front. So if we bring out our 1 over ln of 2, then we get 1 over ln of 2 times the limit as n goes to infinity of 1 over 2 to the n. And now we have something we can work with. So we know that 2 to the n goes to infinity as n goes to infinity. And so this entire fraction is going to be 1 over infinity, which is going to go to 0. Okay, so we have 1 over ln of 2 times 0. 1 over ln of 2 times 0, which is 0. And because 0 is a finite number, we say the sequence converges. The sequence converges to 0. Okay, pretty cool, huh? Wow, so this video is long, almost an hour and 20 minutes. Thanks for watching. Sorry if it got boring.